So, a combination is different than a permutation because the order does not matter. Whereas, whew, wow, that's close. Order does not matter for a combination. So whenever you're making a group of people, right? If I was going to say, for your quiz tomorrow, I'm going to make groups of 3, and one group is going to be Jack, Emily, and Julia, and Emily says, I don't like that group, and I say, I'll make a new one. I'm going to make Julia, Emily, and Jack. She'd be like, that's the same group. So when you make a group of people, the order doesn't matter. Or if you're going to make a committee, if you just change the order on the committee, then it's still the same committee. Yes? Ooh, yeah, they should be called. Why aren't combination locks called permutation locks? That is a good question.
No, it's not at all my question. It's just you didn't raise your hand.
So here is, what was why aren't they called permutation locks? I don't know. Maybe less people know permutations than the word combination? Then maybe people would learn. Maybe. Yeah. So here's our formula. We do have to make one small change here. There is not supposed to be a line there. If you have n objects and you choose all n of them, there's only one way to do that. And if you have n objects and you choose one of them, like if you have 52 cards and you choose one card, how many ways can that be done? 52 ways. And we've seen already that choosing 6 objects from 10 is the same as choosing 4 objects from 10. And if you use the formulas, you can really see why that happens. We also know from combinations that the 2 numbers on the bottom add up to the number on the top. All right, we will stick with purple. Poker hands. Poker hands can get quite complicated, as we're going to see today. But to start off with, they are easy. The order doesn't matter in a poker hand. So you'll just have 52 choose 5, which I think I still remember the number. You can check on your calculator. Purple pen is annoying because every time I write with it, it pulls a blue pen up right beside it, and it just, Committee of 2 boys and 3 girls is to be selected from a class of 15 boys and 18 girls. So we're going to get a lot of combination questions that people get confused with cases questions. Because you need 2 boys and 3 girls. The number of ways to choose 2 boys is 15 choose 2. The number of ways of choosing 3 girls is 18 choose 3. And now people start to think, well, I've got boys and girls. Should I add them together? Because those are my 2 different cases. But they're not different cases. Because a different case is when you count a whole thing, like the whole number or a whole situation. You want a committee of 5. These 2 together make a committee of 5. So we have to multiply them together. Because this is our first decision, which boys are going to be on there. And this is our second decision, which girls are going to be on there. So whatever 15 choose 2 times 18 choose 3 is, if you want to calculate that on your calculator, that'll be the answer. So a group of students must be separated into 3 smaller groups. Group A has 8 students, Group B has 5 students, Group C has 7 students. This question could have been asked as an identical objects question. what I could do is I could have in a hat 8 A's, 5 B's, and 7 C's, and I could have the students arrange themselves from youngest to oldest or shortest to tallest. And every single way that I could arrange 8 A's, 5 B's, and 7 C's, well, how many letters is that in total? That's 20 letters. I have repetition of 8 A's, 5 B's, and 7 C's. That's an identical objects question. But we could also solve this problem using our combinations. Does the order matter when you make a group? No. So you want to make group A. How many ways can that be done? Well, we have 20 people. Wow, that looks like a 20 with a 0. Oh, I can't use that eraser. There we go. Da, 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 da. Okay. 20 people, you choose 8 of them. That will be the number of people that could be, that'll get all the groups possible for group A. How many can be in group B? 12, choose 5. Why is it not 20? Because you've used up 8 of them, and they're already in group A. So we have 12, choose 5. How many can be in group C? Basically, once you've chosen group A and B, right? If you're in the last, which group am I in? You know what? Okay, there's group A, group B, and group C. We've already figured out group A and group B, and you're left. So which group am I in? Group E. Okay. And if you do both of these strategies, they will come out to exactly the same number. In fact, if you want to see how they come out to the same number, 20 choose 8 as a formula would be 20 and 8 factorial. What would the other number be down here? 12, because they always add up to the top one. And 12 choose 5 would be 12 factorial over 5 factorial, and the other number would be 7 factorial. And 7 choose 7 would be 7 factorial over 7 factorial, and the other factorial would be? No, 0. So we play a little bit of cancellation with the bright yellow, because we don't have red right now. See, the 12s will cancel out. 7s will cancel out. What are we left with? 20 on the top. 8, 7, and 5. And what's 0 factorial equal to? It's equal to 1. Okay. Find the number of poker hands with no clubs. Well, if I wanted to guarantee that I'd have no clubs when I hand you a deck of cards, what would I have to do? Take out the clubs. Then whichever 5 cards I give you will guarantee that there won't be any clubs in there. So if 39 are not clubs, and I want to have a poker hand with no clubs, well, I take my 39 that are left and I choose 5 of them, and whatever number that is, here, well, I think it's a pretty number. I remember it being pretty. It is. Look at that. It's a pretty number. 57, 57, 57. Pretty. Are the number of hands that have no clubs. So now we're going to get to an interesting problem. Find the number of poker hands with at least 1 club. And I'm going to become a salesman, because I'm going to sell you 3 pitches for the right answer. But I'm going to tell you this. It might be that all 3 that I show you are not correct. It might be that all 3 that I show you are correct. It might be that 1 is correct and 2 are wrong, or 2 are correct and 1 is wrong. So I'm going to try and sell them to you as if they're all correct. And you have to decide if I'm lying, right? Maybe I'm just a really good teacher and I believe whatever he says, right? Or maybe I'm a really bad teacher and you go, yeah, none of those made sense whatsoever. So we'll see. So I'll have my visual, because good salesman has some visual. So here's a deck of cards. Okay. Number one. Pitch number one. I want to have at least one club. So I'm going to take out the 13 cards here that are clubs, and I'm going to choose one of them from there. Chose the 6 of clubs. I'm going to put that one aside. Now I'm going to put the clubs back in the deck and mix them up again. Okay? And I am now going to choose, how many cards are left? 51. I'm going to choose 4 of them because I could get more clubs. I could get no clubs when I choose those extra 4. And no matter what, because I already picked one club out, I'm going to have at least one club. Method number 2. Well, we just did in part A figuring out how many hands have no clubs. So I'm going to use the not strategy. I'm going to say all of the possible poker hands we have figured out before is 52, choose 5. The bad ones would be the 39, choose 5 that we did in part A, because they have no clubs. So if I take all the hands and subtract the ones that have no clubs, then I'm going to be left with at least one club. Pitch number 3. I'm going to use cases. I'm going to count things slowly and methodically. Case 1, I'm going to count how many poker hands have one club. So I take my clubs, 13 of them. I choose one club. Maybe I choose that 6 of clubs again. Then my other 39 cards that are left, so this is one club. I have to choose 4 other cards, and this will count all the ways that I have one club and 4 other cards. Case 2, 2 clubs. Well, now I take my 13 clubs, I choose 2 of them. Of my 39 that are left, I choose 3 more. What do you think case 3 is going to be? Case 3, we're going to figure out 3 clubs. And so we'll have 13 choose 3 times 39 choose 2. How many cases are we going to have in the end? 5 cases, because we have to do 4 clubs, which is 13 choose 4 times 39 choose 1. And finally, case 5 with 5 clubs, 13 choose 5. With cases, once I figure out each of those numbers, I add them up, and I'll get my answer. Those are 3 ways to figure out at least one club. Now you have to decide, do all 3 of them work? Does only one of them work? Do none of them work? Are 2 of them right? What do you think? So we have a problem someone mentioned in the first one, that if this is bigger than 52 choose 5, this would mean that there are more hands with at least one club than there are poker hands, which seems to be a problem. So strategy number 1 seems to be one that we can rule out as wrong. I thought I sold that one really well. Some of you actually wanted to buy strategy number 1, and it was on sale. Just for Boxing Day, yeah, coming up. Christmas. What about strategy number 2? It's a different number. It's possible because it's less than 52 choose 5, so at least it's a possibility. But is it right? Does it make sense? That if you took all the poker hands and subtracted the poker hands with no clubs, all the poker hands that would be left would have at least one club. That makes sense? What about the last one? Doing all the cases. Has anyone added them up? That is a lot of work, eh? You have to do each case separately and then add them all up. The third one is I'm looking at the cases where I have one club exactly. So 13 choose one, chooses one of the clubs from the 13. Then the 39 cards that are diamonds, spades, and hearts, I choose 4 of those. And that would be exactly, case 1 is exactly 1 club. Case 2 is exactly 2 clubs. Case 3, exactly 3, exactly 4, exactly 5. And if you add those all up, you'll have all the hands that have at least 1 club. So I see that some people are adding them up. So we need to explain why the first one doesn't work. I'll tell you right now, you're going to add up the last one. You're going to get the exact same answer as the second one. And in fact, the second and the third one are good strategies. But the question is, the first one sounded good. I would think of something like that. How do I catch that mistake? How do I realize that the first one is wrong? The first one is wrong because we have introduced order without knowing it. Okay? And the reason we've introduced order without knowing it is I gave an example of, realize how often I want to switch colors when I teach. That sticking with purple the whole time is causing me grief. Anyways, I'm going to switch to blue. So here we go. If I do 13 choose 1, I could choose the 6 of clubs, and then I could have got the ace of hearts, the 7 of diamonds, the king of diamonds, and the 5 of spades. No, I don't want the 5 of spades. Oh, that eraser doesn't work either. Here we go. I could have got the 5 of clubs. Yes. Can you see that that's a possibility? That in my 13 choose 1, I choose the 6 of clubs. And when I put all the cards back, those are 4 things that I could choose. Now, when I did the 13 choose 1, could you see that I could have also got the 5 of clubs to start with? And after I put the cards back in, I could have got the ace of hearts, the 7 of diamonds, the king of spades, no diamonds, that's a diamond, and the 6 of clubs again. And in this method, in method 1, that's counted as different. But those are the same poker hands. So we notice that we have an overlap here. That we can choose the same card in 2 different places, and because we do that, we create an order. We could have chosen the 6 of clubs first and the 5 of clubs in the second pile, or the 5 of clubs first and the 6 of clubs in the second pile. And so we've counted a number of poker hands twice, or 3 times, or 4 times. And in doing that, we got a number that was bigger than the total amount of poker hands possible. Notice in the cases, when I broke up the cases here, this was fine because there was no overlap. I did clubs on their own. I did the other cards on their own. And so that is a legitimate way of counting things. But as soon as you have an overlap in your cases with combinations, you are creating an order at that time. All right. This afternoon, we will look at more poker hands. But for now, we will work on our combinations worksheet.